deriving properties of this Radon equation, let me once more come back to the physical situation to which it applies. So for every direction, for a fixed phi, you will get a function of p on the line. That's what you measure for a fixed angle. And now you change your angles, and then you get a function of two variables, p and phi. And that's what is here. If you change phi to phi plus pi and p to minus p, you get the same line. So it sort of suggests that the function you get will be even in p. What else can we say? This map F to G is obviously a linear map. So we write down formally G is equal to FRP, where G are functions defined on R, and F are functions on R2 in the plane. Obviously, if F is continuous with compact support, the same will be true of G. Moreover, as long as you work with continuous functions, you will have G of phi p equals to G of phi plus p pi p. Because G is a function which is continuous on the circle. If you go over to just integrable functions, then this continuity, this periodicity plays no role anymore. So first, property is that R maps L1 R2 into L1 of 2 pi times R. And this map is a bounded linear operator. If you don't, or you have forgotten what bounded linear operators is, you will see it in the course of the proof. So this is the first more general assumption on f. F should be integrable. Why this is natural? Why? We have to do with attenuation, with absorption. And absorption, in fact, is always proportional to the density. And density should be integrable because it goes the whole mass. So that's the reason. Huh? There is also one thing we didn't mention and which is somehow there, that this attenuation f is a property of a point x and not on the direction in which the array comes. So we suppose that the material in this sense is isotropic. Can be materials which are not so, like crystals or something like that. They have different properties in different directions. This isotropy is inherent in this law, which we put here. So this attenuation depends only on the place where you are. F of the place, and not on the direction. So, so to look at that, we would have to look at the integral. Integral over R2 f of x dx. This is finite by supposition. But now, I can now introduce new variables for a fixed phi. Fixed phi, and then fix a theta. And those variables are this is the transformation of variables. It goes into p theta plus s theta t. So instead of x1, x2, I have the new variables p and s. This is a new orthogonal coordinate system. And this is equal to cos phi sin phi minus sin phi cos phi ps. P times theta is this. P R times theta is P cos phi P and phi. And S times theta orthogonal is equal to S minus S sin phi S cosine phi. Now invert this function and you get this. Yes. So, now this transformation of coordinates is just rotation. So I can write down the measure dx to equal to ds dp, because it is the Jacobian is 1. So this is then equal to r dp r f of p theta plus s theta ds. This is allowed by the theorem of Fubini. You can integrate repeated integration in one direction. First over p and then over s, Fubini. In particular, that means that this function here, as a function of p, exists almost everywhere for almost every p. But now, this can be rewritten. This is just R F phi p. So this is equal to dp R F phi p. The function is integrable. That means that also Rf is in L1. The same argument shows that we would like to estimate the norm of this. So we would like to look at integral over R dp integral over R f p theta plus s theta orthogonal ds. So we look at the L1 norm of the mapped function. This is again now less or equal than R dp R f d theta plus plus S S. It is nothing else, changing the variables once more. Now, the G 1, you have to integrate absolute value of G over P and phi. But this is constant in phi. So it is now 2 pi 1. So the map we can write down RF 1 is less or equal than 2 pi F 1. And that means that this operator R is bounded. That's the definition of boundedness. That of course means that mapping F to G is a sort of correct. Small changes in F will produce small changes in G. Well, but regrettably, that's not the direction we are interested in. We are interested in the opposite direction. We would like to know how F depends on small changes in G, because it's G we are measuring, and F is unknown. And that's much more difficult. And this is the real issue with Radon transform. It is an integral equation. But it is unlike classical integral equations. You certainly have met some of them in your study, some integral equations, but they look always this way. You have G is equal to some G0 plus RF. And this is quite a different thing. This had to do with Fredholm. And if this is 0, then it has to do with Volterra. These are just the names which are attached to these types of equations. And Volterra is much more tedious. Okay, so that's what we know. We have proved first that this map is continuous in L1. Five, yes. I mentioned that the map is even, or that the result is an even function in a very special sense. That means that R of F phi plus pi minus P is equal to R F phi P. that's the property which is, well, obvious. The next, I will now list a bit some elementary properties of this equation or this map, which will then facilitate deriving important facts about it. Okay. Why this evenness is important? Well, we should know where the inverse would be defined. So this map doesn't cover the whole space. Anyhow, it's less than that. It's even more, but it's quite enough. Let me just make one more remark. In numerically solving such a problem, what you will do, you will discretize and get a matrix and invert a matrix. That's what we'll do. Integral will be approximated by a sum, and then the function will be approximated by a sequence, by a vector, and you will get a linear equation. Easy. But all those bad properties which you have here will not be lost. It will be mapped into what? Into bad solvability of this linear equation system. The matrix will be very badly conditioned. And we will have to fall down again to our problems with singular values and throwing away non-significant components and so on. But you don't know, your knowledge now is too little to be convinced how bad this map is. And I will try now to somehow to derive this badness. Well, but before that, I would like to prove a new key identity. Somebody tells it slicing. And this is the following. Integral over R f phi p dp is equal to integral over R2 f of x excuse me, there is some more function here. H of p dp is equal to integral over R square f of x h of theta perpendicular depending on phi scalar product which x dx. Well, you know, scalar products between Euclidean vectors in my notation are just omitted. You just write one vector beside the other one. But if you will, to be quite precise, then I will put a dot. Which is just a scalar product. That's the identity. Valid for f from L1 and h from L infinity. So just bounded measurable, anything. let this stay because this is definition of our map. So, for a fixed phi, set f of x is equal to small f of x times h theta t perpendicular of phi times x. Now, L1 times L infinity is again L1. So it's integrable. So I have now integral over R2 f of x dx, which is equal to R square h of theta perpendicular of phi times h dx. Now again make the same transformation of variables. Go over to P and S. That will give us f of p theta plus s theta perpendicular ds dp, which is equal to integral of dp integral of r f p theta plus s theta perpendicular times h theta times, now x is equal to p theta plus s theta perpendicular. That's what it is. ds. Now, this is just p, because theta times theta perpendicular is 0, and theta times theta is 1. So this gives integral dp over fp theta plus s theta perpendicular h of p ds. But this can also be written as x. So it is nothing else but f of x h theta t times x dx. And this is this here. Well, this is a technical lemma, which enables us to establish a fundamental relation of a random transform with another transform, which pops up everywhere in mathematical life, and that's the Fourier transform. Connection R with F. F is 1 over 2 pi n half integral a to the minus I x psi is the Fourier transform in Rn. And this function, the mapped function, is usually called f hat of psi. Now this transform, when you forget everything about Fourier transform, the only thing you should not have forgotten is this formula. And it's quite enough. There are not hundreds, but thousands of scientific articles written about the Fourier transform. How? Well, they treat different environments in which this transform is working, different classes of functions, L2, LP, Schwarz functions, distributions, anything else. But a practitioner sees only this formula, and with good reason. We need those theorems about how this map is behaving between different classes of spaces. Okay. But it is summing up different exponentials with certain coefficients. That's what it is. A more general way would be e to the minus e x psi d mu of psi, where mu is just a measure. Now, this encompasses Fourier series or discrete Fourier transform, finite measurable, everything is in this. That's how a mathematician sees that. But the practitioners still keep at this formula with good reason, as I said. That will be the topic of the next lecture, and you will see how Fourier transform. Well, I would still again use my comparison with the magnifying glass. The Fourier transform is a magnifying glass to look into the structure of a matrix, of a differential equation, of an integral equation, or anything else. Because it is eigenvalues and spectral decomposition. Separate the essential from the non-essential. So thank you for today. And I lost my voice anyhow.